Good day, folks. Welcome to video lecture number 3. We'll be covering chapters 3.1 to 3.6. We do omit 2 sections out of this. There's a small section called Chebyshev's theorem, and that's on page 110 to 112. We won't be doing that. As well as the whole section on 3.4, working with group data, and that's on pages 113 to 117. So we won't be doing this. We will be looking at the other rest of the sections in the chapter. If the video is too long, I'll break it into 2 parts. So as usual, we'll be using the Pearson's Business Statistics book. So the first concept we come to is called central tendency. So central tendency is a single value used to describe the center point of a data set. So there's 3 words that they use in this section. The first one is a mean. The common word that we use in everyday language for the mean is called the average. Okay. The next term is a median, and then the next term is a mode. We can also have what's called a weighted mean or a weighted average. So the idea with central tendency is that when we have a large population, and we're measuring a certain characteristic, like let's say height. Okay, so let's measure adult females for their height around the world, right? There would be more people towards the middle of the data. So there's a lot of people around the average height, but you don't find many people that are 7 feet tall or 8 feet tall, right? Or many people that are on the other end of the extreme, 3 feet tall or 2 feet tall, right? That were adults. So most of the scores are in the middle. So that's why they use this term central tendency. So the first one is the mean or the average, and it is the most common measure of central tendency. And so to calculate the mean by adding all the values in a data set and then dividing the result by the number of observations. So if you have 3 exams in this course, if you wanted to find the average score, you would add all your raw scores up and divide by 3. Okay. So depending on how large your sample size is, what they have is to calculate the sample mean, which is this X bar. That's how it's pronounced. Okay. Then they have this funny looking sigma sign, Greek, I equals 1 on the bottom to n on the top. And they have xi fraction line with an n. So this funny looking sigma sign means the sum of. So when you see the sum of xi, literally what it means is x1 plus x2, plus x3, all the way up to xn. You add those up and then divide by the total number by your sample size, and that'll give you the average or the mean. So there's 2 different means that they talk about. They talk about the sample mean and the population mean. So I'm just going to go back to the previous screen here just to kind of tell you what the difference is. Okay. So when we have a large or a population, if we wanted to find the population mean, we would have to set our measure every individual in the entire population, and that would give us the population mean. Okay. Usually we don't have the time, the money, or the resources or the need to sample everybody in the population. So what they do is they just choose a certain number from that population, and then they can estimate things. So if we're going to calculate the sample mean, if we just take 7 people at random and measure their heights, the value that we get at the end would be the sample mean, because it's only a sample of the population. It's not everybody. So they call that X bar. If it's the population mean, they use this uppercase N to denote all the individuals in the entire population that we're looking at. Okay. And it's the same formula. It's the sum of the raw scores divided by the total, but this time they use the letter mu. It's a Greek mu. And when you see this letter, it specifically stands for the population mean. If we look at this example here, they have a sample size of n equals 5, and they give us 5 values. They're not descending or ascending order or anything like that. So in order to calculate the sample mean, we do the sum of the X scores. So you add all your scores together and then divide by 5. You do have to hit equals or put the top in brackets, right? When you divide by the total number at the end. And usually we do this using Microsoft Excel. This brings us to the concept of a weighted mean. So a weighted mean allows you to assign more weight to certain values and less weight to the others. We use this formula if our data has already been broken down into the class and frequency. And so for this formula here, there's this new letter WI, and they're calling that the weight for each data value XI. So what we use is, sorry, I'll just look at the formula and then we'll look at what we're going to use. So it's the sum of WI times XI. That's the weight, each weight times each score on the top, and you add those together, divided by the sum of the weights on the bottom. So what we use for the weights are the frequencies. So here we're given data. Suppose you have already summarized the number of days you worked each week from a sample size of n equals 20 weeks into a table. So the number of days worked, 3, 4, 5, or 6. So those would be our different classes. And the frequency of each of those is on the right, 4, 7, 6, and 3. So literally what that means is you worked 4 days, there was 4 occurrences where the person worked 3 days a week. There was 7 occurrences where they worked 4 days a week. There were 6 occurrences where they worked 5 days a week, and 3 occurrences where they worked 6 days a week. So if we were going to find the average, we would have to add 4 3s together, plus 7 4s, plus 6 5s, plus 3 6s. Okay, so what we do is we use the frequency or the relative frequency for the weights. So again, we have the data summarized in the following chart: frequency chart, number of days worked, and the frequency. So in order to find the average, what you end up doing is you end up multiplying these each set of numbers that are across from each other. So the weight is 4 times 3. The next one is 7 times 4, 6 times 5, 3 times 6. So that just saves us from adding 3 plus 3 plus 3 plus 3 4 times, right? So it's just a shorter way to write the formula. So on top, you multiply the raw score times the frequency and you add them. On the bottom, you add up the total frequency. And so that should be your total N. So if we look at the values that we get, and then we'll look at how we would do this on an Excel spreadsheet. So they multiply each of the numbers together, they add them on top, they add the bottom. 88 divided by 20 is 4.4. So that would be the average number of days worked for this sample size. So we'll look at how to do this question, this type of question on an Excel spreadsheet. So I've put the data in 2 columns. So the days worked are in the left column, column B. The frequency of each is in the next column over. So you have 2 options here really to get the weighted mean. So the formula for the weighted mean is on the right here, where you multiply the weight times each score and add them up. And that's on in the numerator or the top part of the equation. The sum of the weights is on the bottom. So we'll look at both ways to do this. The first way is to create an extra column for the top. So what we want to do is we want to multiply the score times the frequency. So I'll just go equals the score times the frequency. It equals, and so we get 12 out of that. And then we can copy that formula down. And so that's each of the values that we're adding together. Weight 1 times x1 plus weight 2 times x2 plus weight 3 times x3 plus weight 4 times x4. Excuse me. So now what we can do is we can sum those, because that's what's going to be on our top. So we multiplied to get that column. Now we're going to add them, and we get the 88, the same that they got in the other when they did it the long way. We also need the total frequency, the total weight, which is 20. So what we can do now is we can just use the formula above, which so we take the top of the equation, 88, divided by the total. And we get X bar to be 4.4. So that's kind of a long way to do it. You can create the columns or an extra column and then find the total of each on the bottom. Excel does have a reserved equation called sum product. And what it does is it multiplies two values next to each other. So in this case, 3 times 4, and then it adds the column for you. So it would multiply 3 times 4, add it to 4 times 7, add it to 5 times 6. So it's called sum product. So I'm just going to type that over here just to show you. Sum product equals sum product, bracket, highlight our data, comma, frequency. So what that's going to do is it's going to multiply the columns, two columns numbers together and add them. So that's the top of our equation right there. We want to divide that by the total number of the frequency. So that's divided by, I could just go this number here at the bottom because we calculated it, but I'm going to use sum. So usually, if you don't have to do extra columns, oops. Right. So for our equation, we have the sum product of column B and column C divided by the sum of column C. That is the weighted average. So we get the exact same value, this 4.4. So choose either way, or you can do it on your calculator, depending on how large the data set is. So there are advantages and disadvantages to using this quantity called the mean. So the advantages are it's simple to calculate. Basically, you add up all the raw scores, divide them by the total number of scores. And so what's nice about it is it's easy to calculate and it summarizes the data with a single value, right? You know, a lot of times in the media or wherever, just in general, talking to people, right? You hear the words, okay, well, what's the average house price or the average cost of something, right? So that's what they're talking about. They're talking about the mean. The disadvantages are with only a summary value, you lose information about the original data. So they give you two data sets there. The first one, they both have sample sizes of n equals 3. One data set is 999, 1,000, and 1,001, and it has an average of 1,000. If the sample on the bottom, which has 0, 1,000, and 2,000, that has the exact same average. Right? If you add them together and divide them by 3, you get an average of 1,000 each. So even though they're both 1,000, just knowing the mean doesn't help you know what the data looks like how spread out is it, right? There's quite a bit of difference between these two data sets, right? So the value of the mean is sensitive to outliers, and those are values that are much higher or lower than most of the data. So if we have data from a sample set, right, most of the scores are going to be towards the middle of the data. You're going to have you could have ones that are way outside, and those are called outliers. And there's a mathematical formula to decide if something's an outlier or not. The next measure of central tendency is called the median. And the median is the value in the data set for which half of the observations are higher and half of the observations are lower. So when you hear the word median, like the median in a road, it splits it right down the middle. And so half of the data values are below the median, half the data values will be above. So in order to do this, you have to first arrange the data in ascending order. On Microsoft Alex, really to highlight the data, and it's one button. Then you have this value called an index point, and they denote this with the lowercase letter I. And what I tells you is, it tells you the position of a certain data point in the list when it's arranged from smallest to largest. So the formula to find the middle one would be I is equal to 0.5 times n. So all you do is you take your number of total data points and multiply by a half. And what that tells you is it tells you where the median is. So with this formula, I equals 0.5 times n. N is your number of data points. If n is even, 0.5 times n will give you a whole integer. If it's not a whole number, if n is odd, 0.5 times an odd number is will give you a 0.5 of a number. So the rule is to round up. Usually we don't even use that. There's a pretty straightforward rule if there's an odd or an even number of data points. So the first one we'll look at here is if you have an odd number of data points, so n equals 7. So you'll notice the data is arranged in ascending order from smallest to largest. Then in order to find the median, we would go 0.5 times n, we get this 3.5. And because it's not a whole number, we round up. So we use this I would be equals to 4. So that tells you that the median is in the 4th position, starting with the smallest being position 1, position 2, 3, and 4. So with an odd set, the median is really easy to find because it's your middlemost value. So for the median, there's 3 values below 28 and 3 values above 28. So that's why 28 would be your median. So unlike the average, the median is not sensitive to outliers. So they give a really extreme example here. So we have these 7 data points, right? But they changed the last value to 5,000. So I think you'll agree, out of the set of data that you're looking at, 6 of the values are fairly in the ballpark of each other. And then 1 is way out, right? The 5,000. So that's called an outlier. If we were going to include that outlier in the average, right, it would change our score dramatically, right? For the median, it doesn't have an effect on it at all, because all that's important is when you arrange the data, what's the middle value? So the big rule on the bottom, when there are an odd number of data values, the median is always the middle value in the data set. If there's an even value, what we have to do is we take the average of the 2 middlemost values. So again, if we're going to use this index formula that they want to use 0.5 times n, 0.5 times the 6 data points that we have would be 3. And so it says the index number is a whole number, so the median value is halfway between the 3rd and the 4th values. So that's all you need to do is arrange the data from smallest to largest, and you literally have to find the average of the middle or use Microsoft Excel and it'll do it. The last value of central tendency is called the mode, and the mode is the value that appears the most often in a data set. So if no data value or category repeats more than once, then we say the mode does not exist. If more than one mode can exist, if 2 or more values tie for the most frequent. So the mode is a particular useful way to describe categorical data. So that data where we have labels on it. So let's just look at one that actually uses numbers for the raw scores. They could be labels as well. So here they give us a bunch of data. So they give us a list of numbers so n is equal to 24. They give us a histogram on the left with these balls, okay? They put the data into a raw score frequency table. So if we look at which one occurs most often, it's the number 2. So we would call that the mode. So the mode sometimes is not like it's wrong to call it a value of central tendency. Sometimes the mode can be on the outside of the distribution. The mean and the median will always be towards the middle. If n is large, if the sample size is large, the mode should be near the middle as well, but it doesn't have to be. So here they give you one where they use categories, labels for the categories. And for that one, they just pick the most frequent. So given a set of data, you can have 3 different values for the mean, the median, and the mode. So they give you an example here of the prices for 5 homes. So they have one house that's at $2 million, one at 500,000, one at 300,000, and then 2 at 100,000. So if we find the average value or price of a house, it would be 600,000. The median would be the middlemost score. So the data is arranged in ascending or descending order. The middle value itself is 300,000. So that would be the median. And then the one that appears the most is the mode. And that would be the 100,000. So you notice the mode really isn't in the middle, right? But if we used statistics is based on the large numbers. If you get larger and larger and larger sample sizes, eventually the mean, the median, and the mode should all be really, really close to the same value. This brings us to the shape of different distributions. So there's 3 different classes. We can have what's called symmetric. So that would be given by the histogram on the bottom left. So we have our mean or our median in the middle, and that's where most of our data is. And then the scores on either side are pretty much equal. They're a mirror image of each other. So the values above and the values below have roughly the same frequency, the same spread about them. So we call that symmetric. It's like a mirror image around the mean or the median. You can have data that's skewed. So you can have what's called left skewed or right skewed. So the words are kind of opposite of what you think. If the chart is down to the left, so picture yourself skiing down this hill, okay, you would go to the left. So that's why they call it left skewed. Right skewed, you would be skiing down to the right. So that's why it's called right skewed. Okay. Maybe if we look at a data that would be skewed, hockey scores, for example, how many goals a hockey team scores? There would be more scores around 0, 1, and 2, and not many goals around 7, right? So the data, more of the data is squished towards the smaller end. So that would be called right skewed. So you just have to, the best way to look at it is which way you're skiing. You'll have to identify is it left skewed or right skewed. They'll also ask you to identify it by looking at the properties on the bottom of each chart. So for symmetric, the mean and the median are pretty much equal to each other. For left skewed, so that's where most of the data is on the larger side, the mean is less than the median. And for right skewed, the median is less than the mean. All right, so I just made up some fake data to show you this skewness thing. So we have the hours studying. So this is probably for the statistics course here, right? So we have some data points. I created a first frequency chart over here. So we had one occurrence that had 2 hours studying, let's say, 4 occurrences, 3 hours studying, and 10 occurrences, 4 hours studying. So if we look at the histogram on the right, okay, so you would call that skewed to the left because it's down to the left. If you look at the values, if you calculate the average, the mean, it is calculated at 3.45, so roughly 3.5. So that's roughly halfway between 3 and 4. The median, on the other hand, is 4. So if you recall, the median is the halfway point of the data. We have 15 data points. So the halfway point would be the 8th element. There's 10 in 4, so 4 is the median, right? So if you look at it, the median value is greater than the mean, and usually that implies that it's skewed to the left. So that's the type of question you'll be asked. This brings us to the Excel functions in the that you can use to find the mean, the median, and the mode. As well, there's a data analysis tool pack. You can use what's called the descriptive statistics, and it'll calculate all 3 values at once for you. So on the right side of the screen, in the Excel spreadsheet, they show you the 3 reserved words or the 3 formulas that you can use to calculate each. You can shorten the bottom one a little bit. So you can find the average. So you type in the word average, put an equal sign, bracket, and highlight your data. It equals, and that'll give you your mean. Same type of thing for median, equals median, and then highlight your range. And the median pops out. For the bottom one, you don't have to put the .sngl in. You can just type in the word mode, and it'll pick the mode. So some notes on the bottom of the screen here. If there is no mode, Excel displays a hashtag NA. So it's just because if they all occur the same amount or no one's the maximum, it'll just return that. Okay. If there's more than one mode, Excel will incorrectly display only one mode, so use caution. So I did try this, and that's true. If there's more than one mode, it'll only find one of them. So if you're doing a MyLab question, make sure that you don't rely on that. Like, actually look at the data, and we'll show you how to sort it and all that stuff so you can identify it easily. Okay. And Excel will not identify the mode for a categorical data, so it has to be a number value. So this is found in the same place as we used in chapter 2. In the data tab up top, and you choose data analysis. When the box comes up, you choose descriptive statistics. And it works really similar to the histogram one. The box's layout's really similar. So you highlight your range where your data is. So that's all your raw scores. You can't use descriptive statistics if your data is already in a frequency chart. So this is just for a list of 20 numbers, 100 numbers, etc. Okay. So you choose your input range. Column should be default. For our output range, you can either pick a new sheet or you can just pick a cell in that sheet, usually just to the right. And then the one you want to make sure that you hit is summary statistics. So when you hit that button, all of these things pop up. So it gives you more information than you need. But the mean of 3.25, the median of 3, and the mode of 1 is picked right off of there. It also gives you other values. We're going to use some of them in later sections, and we're not going to use some of them at all. We'll look at an example of how to use both the reserved words of average, median, and mode, as well as the descriptive statistics. So here, I just made up some data. So drive time to work in minutes. So I have data here. I'm just blacking it out. So there's 9 values altogether. You'll notice that the data is not sorted. So you want to make sure that I would double check just to make, I would sort it no matter what. So I'm going to make my screen smaller here so I can actually see my buttons. And so you want to go to data. And what pops up is in this sort section here, there's a big sort button. If you have more than one column, you can sort a whole columns with one value. The one we're interested in is the top left where it says A to Z going down. So I'm just going to hit that button. And what it does is it sorts it in ascending order. So once that data is arranged in ascending order, you can find all the values, or you don't really need to sort it. I would suggest you do if it's not sorted already. So over here, option one is to just use the reserved math functions. So you can find the average, type in the word average, highlight the data. Same type of thing for the median. And then I find for the mode, all you really literally have to plug in is equals MODE and then bracket for the purposes of what we're doing. Okay. And it picks the mode off. What you'll notice is that if you look at the data, there's two occurrences of number 11 here, 11 minutes to drive to work, two occurrences of 18. Okay, so there's a tie for the mode. What Excel does is it gives you the one that it finds first. Okay, so that's why I'm saying you should rearrange your data and don't rely on Excel because it's only going to give you one answer. So that's option one, is to just type those in. That's pretty straightforward, right? You can use the descriptive statistics toolbar. So we go to data analysis. Oops, sorry about that. So we want to highlight our data first. Data analysis, descriptive statistics. And I'll just double check that to make sure that our range. If I didn't highlight the range first, you can always just highlight it. It's in columns already. The output range, I'm just going to put in cell H, so just over here. And you want to make sure that summary statistics are turned on. So that's really nice. In one little box there, we have the same values. So we're going to look at standard deviation, things like that in a later section. So when you're doing this, you have an option to use the data analysis toolbox that's given to you here, or plug in the reserve functions. Either way, though, pay attention to the mode because they'll try to trick you. So out of these three values for central tendency, which one is the best? So depending on what kind of data you're looking at is the answer to the question. So the mean is generally used as it is relatively easy to determine and most widely understood by people with little statistical training. If outliers are present, the median is often used since the median is not sensitive to the outliers. So if you recall that example where they had a 5,000 out of nowhere, right? That would greatly affect the mean, but it wouldn't affect the median. So in a lot of places, for example, what they'll do is they'll give you medium home prices, maybe reported for a region, given it's less sensitive to outliers. So houses that are way overpriced or way underpriced. And then for categorical data, mode is the only choice. So on the table, they give you the advantages and disadvantages of each. So those could be asked on a multiple choice question. So looking at chapter 3.2, measures of variability, show how much spread is present in the data. So far what we've looked at is values of central tendency. Those gives us a number in the middle that describes the data. What this section does, it describes how spread out the data is. Okay, so the words they use range, variance, and standard deviation. Each of those for a sample and a population. So the range is the simplest measure of variation. And what it is, it's defined as the highest value in the data set, subtracted minus the lowest value, excuse me. So in this data set here, we would subtract 13 minus 1, and we get 12. Might be able to see the problem already. Okay, so the advantages, it's easy to calculate and understand. The disadvantages, it's only based on two numbers in the data set, and it ignores the way in which the data is distributed. And it's sensitive to outliers. So the outliers are on the extreme left and right ends of the data. And so in the two examples that they give you, right, the one on the bottom has a much larger range because of this outlier. So if you're just going to deal with the range, you have to take that into account. So a better description of the spread of the data, instead of just using the range, which could be affected by the outliers, is a thing called the sample variance. And it's denoted by this S squared. And they have the formula on the box on the right. So S squared is equal to the sum of xi minus x bar, and you have to square those and add them, divided by n minus 1. So if you look at this formula, what it's saying is it's saying find the average, the sample mean, then take each of the scores, go xi minus that mean, and then square them. So that means that each of the terms is going to be positive because you're squaring them, and then you add them. So you're going to add a bunch of positive numbers together and then divide by n minus 1. So that's what's called the sample variance. And we'll look at some examples of that. Excuse me. So Microsoft Excel will do this really quickly for you. Okay, we are going to go over the theory of, or if you had to do it by hand on a calculator, on what it would look like. So in this data set here, they give us n is equal to 8. The scores are arranged in ascending order, and they figured out for us that the mean is 10. So they put this box in the middle of the top here just to show you that they didn't show all the values, but literally it's 4 minus x bar squared plus 6 minus x bar squared all the way on top, so you get the idea. And then you divide that by n minus 1. So on the top, you're always going to get a positive number because you're adding things that are squared. Every value is a positive, whether it's below the mean or above the mean. And then you divide that by 7, and you get this value of 18.571. So we'll look at an example here of how you would do the sample variance kind of log way in Microsoft Excel. Then we'll show you the way to push the button and get it. Okay, and then I'm also going to explain why we use n minus 1 on the bottom for the sample variance. So for the sample variance, you'll recall they denote as s squared. So that's just for any sample size lowercase n. The population variance, on the other hand, same formula, except they use an uppercase n on the bottom, and there's no minus 1. Okay, so you just have to watch on what they're asking you. Okay, so for this first part, we're going to deal with the sample variance. So in order to do that, we have to find the mean and then subtract each raw score from the mean, square it, and then add them, and then divide by n minus 1. So I just made a little chart here. The index is the place value of the data that we looked at in the previous example. And then this x, I'll make it xi. Just so it's clear. So those are our raw scores. I did count the elements using count, and there's 9 of them. And I found the average or the mean. Let's use the average function. So that's what we'll use in our calculation. So what we want in this column over here is equals, and then we want to take each of the raw scores, so one cell to the left, minus the mean, and we want the mean to be the same for all of these cells. So once you get to cell H5, in this example here, I would hit the F4 toggle button, and you'll notice how the dollar signs came up around the H5. So that, again, makes it an absolute reference. It's always going to keep that cell if you copy the formula. End bracket, and then we want to raise it to the square. So you use the caret above the 6 and hit square, or hit 2, sorry about that. and hit enter. Hit enter. So what that did was it subtracted the 3 minus the average, and then it squared it. And then I'm just going to copy that formula down. So you'll notice all these values that we found in this column are positive, and they should be because what we did was we subtracted scores and then we squared them, so they have to be positive. So we want to, for the top, we want to get the sum of those. So I'm just going to sum them on the bottom here. Sum those. And so really that's our top of our equation. And then what we want to do for the rest of our formula, to find s squared. So we want to take that value that we found, the sum of the squares on differences on the squares on top, divided by n minus 1. So I'm just going to put a bracket, then go to that cell, minus 1, n bracket. Okay. And we find a sample variance of 27 points. All right, so that's the long way to calculate the sample variance. We could use just the descriptive statistics in the data analysis, so I'm just going to do that here. Data and data analysis. And we're going to pick descriptive statistics. The input range is, we highlight our raw data. We have our output range. I'm going to make the output range down here. And we want summary statistics. So when we look on the chart for the table for descriptive statistics, under the sample variance, we get a value of 27. So a lot of times students ask about why do we use this n minus 1 on the bottom? Okay. And it's based on this idea of degrees of freedom. So when calculating the average, we divide by n, that's the total number of independent data points. So it's what's called, there's n degrees of freedom for determining x bar for the average. When calculating the sample variance, though, we use the data points, the n data points, and the sample mean that we calculated. So given the sample mean also depends on the raw scores, once the mean is known, we really only need to know n minus 1 of the points, because the nth point must be the value it is, or the mean would be different. For this reason, there is only n minus 1 degrees of freedom, so n minus 1 should be used. So on this list here, we have our raw scores. Out of that, we determine the mean. If I change one of these raw scores, it's going to change the mean. But if I know 8 of these points and I know the mean, I can determine the 9th point, right? I could just kind of work backwards. So that's why we would use n minus 1 on the bottom. If you were going to do a descriptive statistic that used another calculated value after that, like if we were going to calculate something using s squared that we use, we would use n minus 2 on the bottom, because now we have 2 less degrees of freedom. Now that we've learned how to calculate the sample variance, denoted by this s squared, that brings us to the next value called the standard deviation. And it's really easy to get from the variance. The standard deviation is the square root of the variance, and it has the same units as the original data. So you probably heard the word standard deviation, right? And so variance, s squared, doesn't have the same units as the raw scores, but when you square root it, that quantity will have the same units as the raw data. So you take your S squared value that you found and you just square it. Sorry about that. We have an electronic weigh scale that just decided to beep, 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 beep. Couldn't figure out what it was. All right, so they give you an example of how to calculate the sample standard deviation. It's really find the sample variance and then take the square. So there are some shortcut formulas, they call them, for the sample variance and the sample standard deviation. If you expand the xi minus x bar squared and you do the math, the formula for s squared, you can write it like in the top box here. There's really no advantage to us doing that because we can use Excel. So if you want to do it, go right ahead, but you won't be responsible for using this. Usually what we do is we either use the descriptive statistics button or we'll do the columns and just add it. So this brings us to the population variance formula. And they use this funny looking Greek letter, it's called a sigma, and it's sigma squared. And you take all your raw scores, subtract them from the population mean mu. You square those, add them up, and divide by the total number n. And that will give you what's called the population variance. So if we look at this formula compared to the sample one, okay, when we use n minus 1 on the bottom, we're making the denominator of the fraction smaller. So the value gets bigger. Excuse me. So what happens is when you take a sample, more of the raw scores are going to be around the middle, and you're not going to have the outliers. Like if you have something that only happens 1 every 10,000 times, right? But you only do 100 data set points, right? You're probably not going to catch that. So for our sample, when we measure the variance, it's going to be smaller than what the actual size is, so that when they divide by the n minus 1, it gets bigger. So it better reflects the actual population. For the purposes of this course, make sure that you're answering the correct question. Are they asking you to find the population variance, where it's n on the bottom, or the sample variance, where it's n minus 1? You do the same type of thing for the population standard deviation formula. You just take your population variance and you square root it. Same units as the raw score. Again, they give you the shortcut formulas if you want to look at them. So they give us an example here of how to calculate using that shortcut formula. They use n equals 6 here. I kind of find it hard to believe that the population is just 6 elements, whatever, right? So just if you were given this question, you would probably use n minus 1 because it's a sample. For this one, maybe for some reason, I think they assume that that's the total population. So just like the mean, median, and mode, you can find the sample variance using equals var.s and then highlight your values. Same thing with the sample standard deviation. You put a little stdev.s in your data values. And that's the one you're probably going to use the most often when you're answering your questions. Usually they give you data from a sample, not the entire population. If you did want to use the population, it's the same start, but then it's .p for them. So again, we looked at this earlier on the descriptive in the data analysis tool. So again, it pops up, it gives you the standard deviation and the variance, Both those values that it gives are the sample. Okay? It also gives the mean, the median, the mode, the min and the max, the count. It gives you the range. So there's quite a bit of information in just that one one. It does reinforce how you're going to do most of your questions, I would think. I would say you're going to get your raw data scores. If you want to sort them, you can using the data sort button we talked about. All you really need to do, though, is highlight the data and use the data analysis toolpack and choose descriptive statistics. So what we can do is we can combine the sample mean and the sample standard deviation together to give us a better description of the data. Okay, so standard deviation is a common measure of consistency in business applications such as quality control. The standard deviation measures the amount of variability around the mean. So basically how spread out it is. The standard deviation is affected by the scale of the data. When the sample means are very different, comparing standard deviations can be misleading. So they use this next value called the coefficient of variation, called CV, and it measures the standard deviation in terms of its percentage of the mean. So a high coefficient of variance indicates high variability relative to the size of the mean, and a low CV indicates low variability, the size of the mean. A smaller coefficient of variation indicates more consistency within a data set. So if we look at the formula for sample coefficient of variation, and then they have the same type of thing for the population one. So if we look at the top one, the CV is equal to the standard deviation S over X bar, which is the average times 100. So this is a ratio of the standard deviation on the top and the average on the bottom. So when you do this calculation, you're not allowed to have any negative values or anything like that. You have to have all positive values, like prices, heights, things like that. Okay. And when you take the standard deviation divided by X bar, it gives you this quantity called the coefficient of variation. So we'll look at an example of that. So the standard deviation tells you relative to the data, how much is the spread? So if we look at the stock price for Nike, they give you the average price last year was $59.67 per share with a standard deviation of $6.64. So when you're thinking about standard deviations, we're going to get into this quite a bit in a little bit. But for most statistics distributions, 68% of the data is within plus or minus one standard deviation of the mean. So for the Nike stock price, 68% of the stock prices that it could fluctuate between are between $53 and $65. Okay, the stock prices outside of those ranges, right, would be less frequent. But within one standard deviation of the mean, it's roughly 68%. Okay, if we look at the stock price for Google, okay, it had a much higher stock price, $1,000.45. And it had a standard deviation of $68.70. Okay, so the same type of thing would go within one standard deviation of the mean. If you subtract and add it on either side of the mean, 68% of the data will be within that one standard deviation. So if we look at the quantity of this coefficient of variation, if we do it for Nike, when we divide it, we get this value of 11.14%. When we do it for Google, we get 6.56. So a smaller number indicates a more consistent price. Even though it has a larger deviation, the $68 is much larger than 6, it's in relationship to the average. So this brings us to the next value called a Z-score. And what a Z-score does is it combines the average and the standard deviation and the raw score into one number called a Z-score. So the formula for that is Z is equal to X minus mu over the standard deviation if we're talking about the population. On the bottom one, it's X minus X bar over the sample standard deviation. And so this Z score is what we use to give a quick and simple value of how far away is the value from the mean in terms of standard deviations. Maybe I'll just go to this slide here and then I'll come back. So this is what's called a normal distribution. And what happens is that we have this bell-shaped curve. And so what we have is the raw scores on the bottom, or the Z score, and how the area underneath describes the frequency, the relative frequency. So within one standard deviation of the mean, this -1 and +1, 68% of the area under this graph is within these two lines. So that would be a Z score of 1. If we had a Z score of 2 or -2 on this curve, okay, then 95% of the data would be within a Z score of -2 or a Z score of +2. So 90% of the data points are going to be between those two values. Only 5% of them are going to be on the tails. So that's where we were talking about if the average height is 5'7", right? You're going to find very few people that are 7'4", right? So they would be on the extreme right end. If you get to a Z score of 3, -3 or +3, then 99.7% of all the data falls within those two values. So let's look at how to calculate this with using some data. So they give us the calories for each burger at different restaurants. And we want to use the Z score to interpret what this means. So if we find the average, the sample mean is this 78.4. They give us a standard deviation of 359.5. So if we wanted to find Burger King that has 1,230 calories, we would take the score minus the average, hit equals or use brackets on the top, and then divide by the standard deviation. So that would give us a Z score of 1.23. So what that means is Burger King's burger is 1.23 standard deviations above the mean. So Z scores are used quite a bit in everyday usage, just because it has this standard. A Z score tells you how many standard deviations a raw score is from the mean. So I'm a golfer. Hope you are too. But if we look at the top 20 major performances since 1960, so they give the raw scores and the total and all that. The column on the right, they give the value in terms of a Z score. So if you recall the previous slide where it said within plus or minus 3 standard deviations is 99.7% of the data, okay? 4 standard deviations is even more freakish, right? So usually the cutoff is anything over 3 standard deviations is what's considered an outlier or outside the norm. So someone that's 4 standard deviations above or below the mean, right, is really an outlier. So the next section on Chebyshev's theorem, we won't do as part of the course. Like I said, it still might be showing up in some of your study plan questions. I'm trying to get it removed. It should take it out because it's not part of our course. So if you do have any of these questions, you won't be responsible. So what we want to do is we want to express X in terms of the average, the Z score, and the sample standard deviation. So if we rearrange the formula for the z-score, maybe if we look at the sample one on the right, S is equal to X minus X bar over the standard sample standard deviation. If we rearrange that equation, cross multiply and add, we get this equation on the right. So a typical question, for a symmetric bell-shaped population with a mean of 20 and a standard deviation of 3, what interval will contain about 90%, 95% of the values? So if you're going to do a MyLab question, they would actually give you values you'd have to state, okay? But we know that roughly 95% of the values are within plus or minus 2 standard deviations of the mean. So if we take our average of 20 and then our z-score of 2 multiplied by the standard deviation of 3, we get 26. If we do the same type of thing except subtract it, we get 14. So with the data that we have, the average is 20. What we would expect is that 95% of all the data we collect between the between the values of 14 and 26. All right, let's look at an example of turning a z-score into a raw score and where this would come into play. So I think we've all dealt with warranties, right? And they seem to, the item you buy seems to break just before the warranty is up, right? Or before the warranty is up, a large majority of the time, okay? And it's not really an accident. The company is doing it on purpose, right? So what we want to do is give you some data here. So you have a vacuum cleaner. The manufacturer expects that the average lifetime of the vacuum cleaner to be 10 years on average, with a standard deviation of 2 years, right? So what does that mean? 68% of the vacuums, right, will break down between 10 minus 2, or sorry, 8 years and 12 years on average, okay? So the company decides, hey, we only want to replace 16% of the vacuums we sell, right? Because we're just going to lose money if we don't. So they have to figure out what should the warranty time be, right? What makes sense as a business decision. So because they decided they only want to replace up to 16% of the vacuums sold, we can assume that around 60% of the data points are below Z equals -1. How do I get that from the chart? So you'll be looking at these Z charts, and you'll be answering questions kind of like I'm doing here with the percentages, okay? But what we know is that 68% of the data falls within -1, +1 for a z-score. So that makes 34% on each side. We know that the total percent underneath this curve has to be 100%. Okay, so if this is 34%, this must be 16%. Okay, so that's where I got a z-score of -1. So if the company's trying to figure out on what they want to decide for a warranty time, so we'll calculate this score. Oops. So X equals. So it's the average, which was 10, plus, and then we're going to put a z-score of -1 in, times the standard deviation of 2. So for this data, if the company only wants to replace up to 16% of the vacuums they make, they should make their warranty time 8 years. Okay? If they go any longer than that, they're going to need to replace more items than they want to. So given we still have about 30 slides left in this section, I'm going to cut the video in half, or cut the video here. We're going to go see Spider-Man. And I will have the second part of the video up shortly after that. So just if you're going through the textbook, we don't do section 3.4, which is pages 113 to 117, which is a lot of stuff. So the second part of the video will start with 3.5, measures of relative position.